So today is the second lecture on this course, Introduction to Astronomy and Astrophysics. Quick recap. What did we discuss last time?
We talked about scales in the different operations in the field of the
Scope of the astronomy.
We have started with the optical.
I asked you to look for the history of astronomy.
Yes.
And what else?
And we concluded with the motivation, final motivation.
Yeah, so the purpose was to motivate ourselves. Are we motivated?
Yes.
Then only we can go. Right, but I can see say, some of the people who could not motivate themselves are not online. But that's okay. That's okay. So today we are going to learn the next thing, but this is not moving. Yeah. So for now, I'm on the second slide now. People online can confirm that is it showing them or not?
Yes, sir.
Yes, sir.
Oh, fine. So lecture 2, we are going to discuss the astronomical instruments, which is very, very critical, right? As far as studying the objects in the universe are concerned. So we will first discuss the radiation and spectra. All of us have some idea. We will try to revise those concepts and have a discussion. Then we will go to the most important tool in the astronomy. That's the telescopes. And this lecture, today's lecture, has been taken from chapter 5 and 6 of this book, OpenStack, which is shared in this Google Drive folder. So my recommendation, even if you are not going to study astronomy and astrophysics in future, read this book. This is worth reading, right? I will say a masterpiece, writing masterpiece. How to explain something to the people who are generally not expert in the field, or just to improve, enhance the, well, say, interest also in the course, right? So this could be kind of a teaching guide also. How to teach your students something. Anyway, so this is not the lecture plan actually, but this is the overall lecture plan also. I've written the two words here: active diagnostics and passive diagnostics. Any idea what they could be? What could be the active diagnostics? We want to study something. It could be some system, some object, whatever. So how do we study? There are two ways. Either we collect the information it is giving to us, or
We perform something on that.
yeah, we send some signal and then see how it reacts to that signal. So that is in some way also known as the perturbations, right? You have a system which has its own equilibrium, its property and everything. You try to slightly perturb it and see what happens to those perturbations. Do they produce a wave? Is there any instability? Or is there a damping to the perturbations and so on? So in the active diagnostics, the same way. You have a system, you want to study it, and you send some signal. So you're diagnosing the system actively, right? Most common example could be when you measure the temperature of your body. So you take the thermometer and you put it inside the body, right? So that's an active diagnostic. You can really put in contact the system or signal to the system you want to study. Under the condition that size of thermometer should be much, much smaller than the size of the body. Otherwise,
Thermometer will have its own interaction.
yeah, and you will not be measuring the actual temperature of the body, because some of the heat, not some now, a large amount of heat will flow from your body to the thermometer itself. They will try to come in thermal equilibrium. So the body which was at higher temperature will come at the lower temperature. So now you are measuring the lower temperature. That's why your thermometer should be very, very small, so that the whatever heat flows or whatever the reduction in the temperature is, it's very, very small. That's the one thing. But in astronomy, we cannot do that. We cannot take the thermometers to the stars, right? Put it there and say, oh, this is cold or this is hot. That we cannot do. We cannot even reach the sun also, right? Why? Whatever spacecraft we carry, it will. We don't have any material which has melting point higher than that of the temperature of surface of the sun. But now people are sending probe, Parker probe. They are trying to study that. But still, it will be very, very far away from the sun. So we have to depend upon these passive diagnostics. That means we have to depend on whatever they are giving to us, right? Or whatever light is falling on us, how they are behaving to that. But we cannot really do anything. We cannot send the light. We cannot shine the torch light on them and see, oh, there's another star. Let's add it to the catalog. That's not possible. We have to depend upon the passive diagnostics. Why? The natural reason. So they are very, very far. Even the nearest star is 4.3 years away, light years away from us. We really cannot do. Even if it is cold, habitable, and everything, we cannot. Even if the colonies, maybe set by some Elon Musk or something, we really cannot go because it will take 8.6 years to go and come back. So we have to depend upon the passive diagnostics. The passive diagnostics means sub-signal must be already coming out from them. And those objects are generally the stars. And if everything else shine because of their light. So that is the main purpose. The main purpose is now, because we are getting this light, how to collect this light. And then how to process that light and how to analyze that. Yeah, separation, the word. We will find the right word for that. Right? So that is the whole purpose of this. So now what we should learn, why that light is generated. What is happening inside the star to generate that light. Right? And how we can collect that light. What kind of techniques we will need to collect that light. And what we can learn from that collected light. That's the purpose of this lecture. So what is this?
It's like an infrared image of the sun.
Yes, this is sun. This is image of sun, but not the infrared. Ultraviolet. Ultraviolet.
Yeah. There is a magnetic activity.
We don't know. So we don't know. That's what we will try to understand. Why sun will give ultraviolet light? Why can it give some other light and so on? But just let's just stay to the very, very basic things. So how is it possible? We cannot see the ultraviolet light, can we? No. Then how did we get this picture?
There are some objects we can use to separate comfort. Ultraviolet light can have its own energy, and we can detect its energy.
Right. So what we are doing, we are seeing what is the energy outcome from the different part of this sun, whatever we are seeing, and then we scale that energy to the color. Maximum is given some color, and then lower one is given some other. The color scheme is used that maximum should get red, and the lowest one should get blue. That is up to us. Right? This is not what we are actually seeing, but this is just on that scale, color scale. Similarly, can we have other photographs of sun? This is UV photograph. Optical photograph. Our eyes we watch that.
We can have monochrome photograph for better.
Yes.
And
What?
X-rays.
There could be X-rays. There could be gamma rays. Could be. I said could be. Not sure. X-rays, gamma rays, UV, infrared, optical. But we know for sure that from sun we get two kind of light. I'll say light now instead of waves or EM waves and light. I will use it. So at least optical, visible, and the infrared. How do we know that there is infrared?
It has
Yeah.
infinite.
Leave this AC room and then go to the lawn. You will know that infrared circle. So for that, we need to understand the light. Let me call it radiation. Right? We know that they are electromagnetic radiations. So that is very, very critical to understand the full electromagnetic spectrum. Right? So what is light? And then we know the current understanding also says that it is not just a waves. Right? It was given by the Maxwell in his equations. Right? 4 equations. And they give us the wave solutions. If you remember, can you tell me how do we get to wave equation?
If you have vacuum, then all the sources vanish, and one of the methods to obtain the wave solutions can be to take the curls of both the curl equations.
Right. Take the curl of 4th equation, use the 3rd equation. Use all the, you will get an equation. Del 2 psi by del T2 is equal to C square into del 2 by del x2. That's a wave equation that tells that there is a wave and it will be traveling the speed of light. That we learned in the classical electrodynamics. That last question somebody asked me, that is there any theory for dark matter? Yeah, there could be any quantum theory, right? Similarly, we have classical electrodynamics and we have quantum electrodynamics also. That is a more reasonable treatment of. But we know that most of the phenomena they can be explained by the classical electrodynamics. So unless we are really doing this complete field theory also. So that's why we study classical electrodynamics even today. Don't go to quantum electrodynamics, which really treats the light as the photons as the wavicle, wave as well as particle. But in classical electrodynamics, we know it's wave. So whatever property, whatever phenomena we see, let it be diffraction, refraction, reflection, interference, they all can be explained by treating the light as waves. Right? So QED we will not talk about. So yes, and then it is really required to know how the different lights originate, different band of the electromagnetic spectrum, and how they propagate in a medium, and how they interact with any intervening object in their path. Everything is very, very important. Otherwise, we cannot build any detector or something. Right? So this is very, very critical. And we have to keep this also in mind. I goes as 1 by r square. And that's the main problem. Because objects are so far away that the intensity is very, very poor. We cannot see them with our unaided eyes. So for that, we need to develop the telescopes. We will see what is the primary job of the telescope, right? But before really going to that, let us discuss one very, very important phenomenon. Is there any connection between radiation and temperature?
Yes.
What is that?
The way that
Do you remember that important curve or phenomena?
Yes, the black body.
Black body radiation, right? So what determines that what kind of electromagnetic radiation will be emitted by the astronomical objects? Yes, that you can look at the black body spectrum or the radiation diagram, and then you can see where it peaks. Generally, the black body will emit radiation at all the frequencies, right from 0 to infinity. But then we know there is a maximum. So most of the energy is radiated in that band around that frequency. So black body spectrum is a really, really important, I will say, tool to at least know the temperature of the stars. Right?
So is it like necessary that every plasma phenomena like Planck's distribution,
Every
plasma in the or in sun obeys that Planck's distribution, energy density distribution?
what is Planck's distribution? Yeah, black body radiation.
Yes.
Yeah, it has to be. Even my body also has to do that. Anything which is at some temperature T, it will follow the black body radiation to a good approximation. What is the approximation? That it is absorbing at all the continuous frequency, at least in a continuous range of the frequency. The energy density could be very, very small at some given frequency, but in a band, you get the continuous spectrum. Then you can call it a black body safely. Anything which is radiation. So what happens when you have an environment which is at higher temperature than this body? It will absorb. But when you remove that environment, then it will emit. Natural, right? We know the flow of heat from low temperature to, from high temperature to low temperature. That is bound to happen. Right. So black body radiation is the characteristics of everything which is at temperature.
Sir, hello.
Yes, go ahead.
So the gamma rays are photons, right?
Yes, gamma rays are photons.
So the particle nature of light is different from photon, right? It's not just photons, right?
Proton. Sorry, I did not hear you clearly.
Photons. I mean, when we say the particle nature of light,
Yes.
there we mean photons are something different. Then.
Yeah, particle nature of, so basically when they talk about photon, now they are considering light as a particle. So we know from quantum mechanics, right, that actual representation of anything is basically a kind of localized wave function. If I could draw it somewhere.
Sir, I guess this question was when we talk about the particle nature of light, are we talking about anything other than photons?
Is that your question?
Yes, sir. Yes, sir.
Yeah, so photon, you can say it's a particle which is having some energy is equal to h nu. The visible light is also photon, gamma rays are also photon.
The waves are quantized, so to explain such a term phenomenon.
Yeah, so you can, so it's a particle term, right? Particle physics term. That this is the quantization of electromagnetic field, photon. But it has both the properties, wave as well as particles.
Okay, sir.
Right? Yeah, but generally photon they use to when they are, there are some, they use this kind of language. They say that light sometimes can behave like a wave and it's sometimes like a particle. So when we are doing this kind of thing, we will say that it's a wave. And when we are talking about particle physics, we will consider light to be a photon. So it's a burst of photons coming from this tube light or whatever. But yes, anything, if you talk about proton, then proton has a particle nature as well as wave nature. And how do you calculate its wave nature? By the de Broglie wavelength. Lambda is equal to h upon p. And how do you know that quantum effects will be important? When the size of the particle is comparable to its de Broglie wavelength. Yeah, so there's a length scale. If those length scales are comparable to the de Broglie wavelength, then you have to apply the quantum mechanics. For example, for me, I'm also particle as well as wave. But my wave nature, which comes from the de Broglie wavelength, how much it will come out to be? It will be 10 power minus 39 meter. Mera. Yeah. Come on, nothing can be at rest.
At a much magnified scale.
Now you are really going in, yeah. Now you are really going deeper. Okay, consider that I am walking at 10 meter per second or 10 kilometer per hour. So if you calculate that, it will come out to be 10 power minus 39 meter, and my length is 1 meter. So I can safely ignore that. But for particles like electrons and lights, it is really, photons are not basically particles, right? How do we get the electromagnetic waves? That an electron is oscillating or getting accelerated or decelerated, and which is producing the photons. We will discuss more in a better picture. So it is nothing, there is no particle, it's basically a field, electromagnetic field. That field can be quantized to give you the particle which we call as the photon. So really, it's when you go to quantum mechanics, things become complicated. So let's focus on the classical picture. Yeah, but the true picture is quantum mechanics. But we will not use quantum mechanics until we really need that. Yes. So for us, we will treat the electromagnetic waves or the light as a wave. Right? We will discuss that also. I'm going to do that. So this is the black body radiation. What is the characteristics of this? That its peak is shifting to the right. Right? When the temperature is lowering. So you can see that if the temperature is high, the peak is on the left hand side. And the wavelength is basically decreasing. That means frequency is increasing. So hot star should appear as bluer. And cold star should be appear as red, which is opposite to what we generally, right? For us, yeah, for us something, if it is hot, then it should look red, right? Right. So this also gives you a Wien's displacement law. Lambda m into T is equal to constant. So from there you can measure the temperature. You can know at what wavelength you are getting the maximum energy. What is this? Where do you get this peak? And from that you can infer the temperature of the body. Important. So this is a thermometer. So now coming to the type of electromagnetic radiation, we know that visible light is not the only electromagnetic wave. So for that, we can really refer to table number 5.1, right, in the book by OpenStack. So they tell you that what are the sources, what are the stars which will be emitting only the visible light mostly. Most of the stars they emit in the visible range. But then there are phenomena in the stars which emit in infrared, in X-rays, in gamma rays, and so on. So what should be? We'll discuss that slowly. This is another picture which we know, and we'll discuss that also. What is happening here?
Different wavelengths travel different ways.
Yeah, so they get split because
Because different colors have different
yeah, so they are traveling within the prism at different speeds. So they are coming at different angles and different time. Or you can say simply they're bending. We study in the class 10th, right? So what is this phenomena? Refraction. So at first point, when it is white light, it is entering the prism. So air is a rarer medium compared to the medium of prism, which is a glass. So light is entering from a rare medium to a denser medium. So there's a normal at this point. The light should bend, and it should bend towards the normal. So that's what is happening. But we know that white light is made up of different wavelengths. So different wavelengths will bend at different angles. So when it is coming out again, you can see again. So now it is going from denser medium to rarer medium. And then it will again move away from the normal. And that angle will be again different for different wavelengths. You can see that there's a clear dispersion between the different colors. They get dispersed. This phenomenon is known as a dispersion, which was the beginning of the optics. This was given by Newton. Call it Newton's prism. You simply take a prism and you can see that you get a rainbow kind of thing. Right. But we know that these colors, they really are not simply 5 or 7 or 8. There could be any number of colors depending upon how well we can resolve them. And it is assumed maybe that the female have better resolving capacity between the colors. Men see a fewer colors, isn't it?
The praying stream mantis has the most sensors that you can see.
Right. And colorblind people will not even see that. But what they will see a dispersion, a spread that they can. Right? This is another property we were going to use the spectroscopy. So this is just to show that how the light spreads in the wavelength spectrum. What is this? So then people try to do this experiment with the sunlight. So they observe this kind of spectrum. What they found that yes, there are blue light, green, yellow, red. There are different continuous colors. But then there are some, missing segments, missing region. Had the light been continuous, it was not very, very exciting, right? Because there are all kind of colors there. But these missing things, they gave us some idea. Can you tell me what could be the reason of this missing thing?
The atmosphere.
Atmosphere.
It absorbs some of the
But that atmosphere could be,
sun itself.
but atmosphere could be anywhere. It could be atmosphere of the sun itself, it could be the earth or between earth and sun.
It can be intrinsic to the sun itself, the light which is.
No, because you see that color only at some portion you see those kind of wavelength or missing.
Because the black body would emit each and every radiation.
Yeah, otherwise sun would have not. Yeah, otherwise sun would have not emitted that. It is not the property of sun. Now we are really understanding, right? Something is intrinsic and something is extrinsic. So this missing spectrum could not be because property of sun. It could be property of the medium through which these light is traveling.
Some atoms have come in its path and have
Exactly. They have
maybe in some
scattered it or
areas
absorbed it. We don't know. Right? So people online can interrupt and participate at any time. So this is sorry. This we know from spectroscopy and from in our atomic and molecular physics also. You get some idea. Why do we get the spectrum? So there is a continuous spectrum, and then there are discrete lines also. So there's a continuous spectrum, then there are some missing parts, and then there are discrete lines. So three things we are at right now. We'll discuss them, how we can use them. But before going to that, we know what is the origin of lights or spectral lines from the various elements. What are those?
electrons go from one state to another state of a lower energy.
Yes, that is mainly because of that. That we know the structure of atom is like this, that there is the nucleus at the center of the atom, and then electrons are outside the nucleus. Right? And then we know that Planck did this correction to the Maxwell. I think it was Planck. Planck gave the idea of quantization. I think it was Bohr who did this picture. That there will be quantized orbits. You will not get continuous. You will not get continuous orbits. So now, if you give energy to the atom, the electrons will take that energy, will go to higher orbits, and when they release that energy, and they will release the photons. The energy of the photon will be the difference between the energy levels. E2 minus E1 is equal to H cross nu. Or H cross omega, or H nu. That's what we all know from our quantum mechanics class and atomic physics or something. Right? The origin of light is mainly because of the transition between the electronic level. And why do we get level? Because of the quantization. Right. And let me be a little more mathematical. How do we do that? We will take the Schrodinger equation, time independent, because potential is not function of time. So we can take the time independent equation. We'll plug the potential. That potential will be the electrostatic potential between the nucleus and electrons. And then we solve that equation choosing the spherical polar coordinates.
Get the probability distribution.
I'm talking about the hydrogen atom problem. So we solve it in r theta phi. First we solve the equation of phi. We get the first quantum number. Now we solve the theta equation, and then finally the R equation. We get the various combination of three quantum numbers, n, L, and m. N being the principal quantum number, L being the orbital quantum number, m being the magnetic quantum number, right?
Sorry, magnetic.
So with these different quantum numbers, we can really find out the what should be the orbit or what should be the electron density. Because we will solve for psi, and with that psi we can find out mod psi square dx, the probability of finding the electron in that given region dx. That's how we do the quantum mechanics, and it gives us the quantized energy states. Electron, when it absorbs energy, goes to the higher energy states which are available to him, and then when you remove the source of energy, electron tries to come back. Why? That's the nature, right? We try to minimize our energy. So it leaves that energy and comes back to ground state. And that's how we get the light from this tube light, isn't it? Right? Similar kind of thing might be happening in the stars also. And we know even further, when we talk about nuclear physics, we know that similar to this electron shed model, we have nuclear shed model also. There could be discrete energy level at the nuclear level also. So now when the nuclear transformations occur, then we get the gamma rays, which are much higher and which have higher energy than the visible rays. So we have visible, then we go to ultraviolet, and then we go to X-ray. We know the region of X-ray emission. What is that?
Electron is decelerated by
No. OJ electron. You might have heard about it. So visible light energy kitna hai?
About radio is 1 meter, about order 1 meter.
Yeah, radio wave is 1 meter, which has the lowest energy. And then comes the microwave.
Mega.
What? X-ray.
So X-ray will be
Kilo electron. KeV. What will be the gamma? It is easy.
mega or tera.
N
No, not tera. Sorry, the tera would be too high.
N mega.
You know the pair production. 2 electrons, electron-positron pair.
Okay, so 1 electron is 0.5 MeV.
So 1.02
MeV
MeV.
gives rise to 2 gamma rays. So half MeV.
1 MeV.
Half MeV.
1 MeV is the gamma ray.
In mega.
So 1 MeV gamma rays, KeV is this, and then you get to lower energy depending upon their frequency. Right. So what is really happening? That when you are probing matter deeper and deeper, you need more and more energy. Right. That's what is happening. We know there are other spectrum also, other transitions. What are those other transitions?
Which transition?
There are rotational transitions. So you have molecules, yeah. Especially when molecule, they can have a structure, and those molecules can vibrate.
Vibrational.
So corresponding to those vibration also, you get some radiation.
but like not all of them are sensitive. Right?
They-
Some of vibrational degrees are always.
Those are detail.
Some modes are.
Yeah, there
More
could be.
detail.
Yeah, we are going in more detail. Let's talk about this. So there could be different modes of vibration. So that also gives you the spectrum. And in what range do you get that? Infrared.
NIR.
And then you have rotational degrees of freedom also. And that gives you the radiation in the microwave region.
Do isomeric changes give rise to radiation?
I'm not sure. Yeah, they might be giving, but in what frequency range or in what energy range, I don't know.
By doing isomeric changes,
So we know that it is these are the phenomena which are happening at different scales within the matter, which give rise to the radiation. So now this is wonderful. We want to look at far away from here at the scales of astronomical unit, parsecs, kiloparsecs, megaparsecs in the light years, billions of light years away. But to understand that, you have to understand the phenomena really at what is happening at the nanoscale, angstrom scale, right? Fermi scale. So really, you are now coming back to this scale. You went up there from the Earth to different part. Now you are coming back. You came to the matter, small matter, then to the molecule level, then atomic level, then nuclear level, and so on. Right? Amazing. But to understand those things, yes, you cannot make those objects in the laboratory, but there are many things you can do in the laboratory to understand those objects. Fantastic. Things are dependent, right? Connected. So it's an electronic transition which basically gives you these different kind of radiation and the spectral line also. We'll discuss spectral. How do we get the spectral line? I again want to remind you, you know that Lyman, Balmer, those kind of series, you know. Right? So again, the transition between the discrete and energy level, which gives you the spectrum. Why do they look continuous? Because now you are looking, basically you're not resolving too much. So they look continuous. I gave you the example. Depends upon the length scale. If you're really looking at the finer scale, you will see the things discrete. If you're looking for the larger scale, you will see this as a continuous. But we are still not clear. What could be the reason of missing things? Because something is getting absorbed. So based on that, there could be three kinds of a spectrum. Continuous spectrum, which is being emitted in the form of black body and so on. There could be this discrete spectra if we are really talking about only one element, because we know stars could be made up of different kind of element, but we are only looking for one element. We're looking for element of that spectrum in a given wavelength. For example, if you want to look at the hydrogen, we have done the calculation. Okay, hydrogen lines will be in this wavelength region. We're looking for that. You know the sodium spectrum also, and so on. Absorption के लिए क्या होता है? If we talk about the absorption spectroscopy, that you have some material, you have a source which is giving you a continuous light, then some of these wavelengths will be absorbed by this. And why they will be absorbed?
They match the exact energy transition.
Exactly. So only those wavelengths which match exactly with the transition level of this matter in between, they will get absorbed. The rest of them will go. That's what's happening with the sun. So now you can also figure out what kind of matter could be there in the between sun and earth. What could be the density, whether there could be any what could be the velocity and so on of that matter. So spectroscopy is a very, very powerful tool for astronomy, and it is otherwise also very, very useful and powerful. Right? So we can really talk about three kinds of spectrum. The sun is the source, which will emit continuously in the band, right, from blue to red light. So this is, you expect to get a continuous spectrum, but then what you get these missing lines, which is because of this cloud of gas in between. And then these missing lines are basically these. They will tell you the nature of this kind. Right? So this is a kind of absorption spectroscopy you're doing. Sun is emitting light and some things are missing. The missing things are basically property of this matter. Right? All right. We'll not go to other things, right? There are other things also. We get another quantum number also. Spin quantum numbers. And we know there's the spin orbit coupling. So we get hyperfine structure and so on. Those things you will learn in your spectroscopy. For us, this is clear that there's a transition are happening between electronic level and the nuclear level, and so you are getting radiation in different frequencies. That's it for now. Okay, now coming back to the telescope. So now our motive is to catch that light, collect that light. That will be done by the telescope. So with the telescope, there are auxiliary setup, which are instruments and detectors. A telescope may not be sufficient. Why?
Because we just use our eye to see the data. We cannot.
Yeah. In the ancient time, people used to do. They will watch something and then we'll write some conclusion. Right? So if you lose this document, yeah, then nobody else will ever need to come to know what did this guy observed, what he understood and what he wrote.
He might be color black or something.
Yeah, maybe. So we want to get it verified with other people also, but others can make it. So we want to record it. And to record it, we need instruments and the detector, right? So there's a spectrometer, there's a spectrogram, and there's a spectrograph. So what are these three things? Spectrometer, spectrogram, and spectrograph.
Like, that's the task of that result. It separates the info in that into separate
Right.
spectrograph. Spectrograph just plots through where the discrete wavelength and leaves the spectrum on the discrete spectrum. It will be the absorption business.
Sorry.
The spectrograph gives the data with absorption spectrum. We are looking at
So when you go to a doctor, what does he do? He does the ECG. So what is the full form of ECG?
electrocardiogram.
Gram, not graph.
Yes.
Why he calls it gram? Why not graph? It gives you some pattern coming on printed on a paper. So that's an home assignment. You can learn about it. The difference between gram and graph. Anyway, so the objective of the telescope is it has to collect the faint light from an astronomical source. But the idea is that light is very, very faint, but the idea is that can we collect more and more light? Instead of using one eye, can we have more eyes? And then ask them to add up their observations. This is roughly the task of the telescope. Right? To watch something continuously or for longer duration and so on, so that you can collect more and more light. So the faint objects, you can really make out of things, what it could be. Right? So the idea of the telescope is to collect the light, more and more light, and focus it to a point. That's the prime task of the telescope. Then that focus light is given to the instruments. What is the role of instruments? It can sort that light into various wavelengths and so on, frequencies, whatever you want to do, whatever your objective is. And then finally, light will go to the detector where it can record that, whatever you got seen. We'll discuss that I'll discuss it for GW detector with an example of GW detector. Right. So we want to collect more and more light. Let's go back to your class 10th. What we will be doing?
Is the aperture.
Increase the aperture. A simple answer, right? Increase the aperture, you need to make more and more, bigger and bigger
Bigger.
mirrors or lenses. We don't know, telescope. But now, if you want to make bigger and bigger mirrors, then there are other issues. What is the first issue? Size, of course, money. Right, because ultimately you have to send it to somewhere, right? And then you need high quality optics so that the size is proportional to the maybe some powers of the money, dollars, billions of dollars. So that is the problem. You cannot really build infinitely large aperture. And then you have to send it to there. So there will be payload. Somebody has to pay for it, right? खर्चा होगा ना, fuel लगेगा. Second thing is it is not easy to build them also. It really needs a lots of sophisticated technology and skills and expertise. Because if, let's say, if you want to make a mirror, that mirror should be, first of all, should be very, very clean. Clean means it should be the surface should be very, very smooth. And the mirror material should also be very, very clear. And there should be no bubble, for example, or some any other kind of cracks or aberration, anything. Otherwise, you will totally get different kind of result. Light which was supposed to focus at this point will get focused at another point. If there is even a finest crack,
You need almost perfect curvature.
Yeah, you have to get the perfect curvature in different part of the mirror. So if the curvature is 1 meter here, it should be 1 meter here also. So all kind of challenges are there. You want to make a very, very large mirror, right? But you really need other things to do it. So the two basic concepts to build a telescopes are that you can either use a lens. We know the convex lens, right? What is the role of job of convex lens? That, yeah, the light falls on the mirror, which is parallel light, which falls on the surface and gets focused. The job of the mirror, convex mirror, is to converge the light at one point. That's a focus. तो उस तरह के टेलीस्कोप को हम you call that a refracting telescope, because now light is entering the lens and then coming at another lens. But the astronomers generally do not prefer this kind of technology unless it is really, really useful or unavoidable. Why? Because as I told you, because you really have to make the very good material lenses and so on. So what is easier? To build a reflector. So for that you can use the concave mirror. The light will come parallel and they will get focused to some point. So those kind of telescopes are known as the reflectors. It is easier. For that you need very, very smooth surface. Of course, material is also important. Because the thing is, we know whatever phenomena we are seeing, let it be reflection, refraction, ultimately something is happening at the microscopic level. The light falls on the mirror surface and it is interacting with the atoms of that mirror. And then finally it is getting reflected. So that material should be very, 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 very clear, pure, and is as aberration free. And so if I talk in terms of optics, because ultimately every phenomena is because of the interaction of light with the particles in the material of the mirrors. So in the reflectors, light really does not have to travel too deep to the mirrors. It has to really focus on the surface. That's fine. The reflectors we astronomers prefer to make the telescopes. So these are the pictures which I was just talking with my hands, but this is clear.
So like the reason for preferring reflectors among reflectors can be one more thing, like for lens type of thing, the property of that material changes within that lens. But for reflector, you can have small mirrors at all the curvature parts. Still the properties remains.
Yeah, but is it practical to make exactly same kind of mirrors? You cannot have identical mirrors. You cannot even create the identical transistors also. That is also challenge with the electrons everywhere. Even ऊपर वाले ने भी दो लोग एक जैसे नहीं बना. It's really difficult task.
But it's a more, it's a 2D plane, so we can have much more less differences than in the 3D making of the lens.
Yeah, that's true. So people are doing that kind of optics. They know how to do. But it is really challenging. Otherwise, James Webb Telescope and Hubble, they would have not made such a big news. लोग बोलेंगे इसमें क्या है? You just have to put a reflector. I can do that. Few meter, 2.5 meter long reflector. I can build that. It's not that easy. Right? All right. So these are the diagram which are showing the two principal. So this is basically a lens, a reflector, and this is of a reflector. So this is a concave mirror. Light comes and it gets focused at this point, and this light goes to your eyepiece. That is also another thing, right? So here you can do the magnification and other things. So eyepiece is also part. This is the main mirror, primary mirror. So the idea is to make this aperture bigger and bigger. This one and this one. Now comes that you can collect the light. It could be visible, it could be radio, it could be. So do we need to have different kind of telescope for different kind of light? Yes. lens and reflector may be good, but yeah, idea is good. Reflector, principle is same, but the material may change.
Detection properties.
Yeah, for example, for a radio telescope, you don't want to use mirror. Mirror may not be a good reflector for that radio wave or for microwave, let's say. Why?
Matter is just a reflector. There is the mirror.
We know one of the radio antenna. सबके घर में है, Tata Sky वाला. What is that? It is a reflector. It's a concave mirror. Light, the radiation comes to that, and you focus it to that. What do you call it? Receiver. That gives a signal to your TV. So now instead of glass lenses, you are using a metal for that. But the idea is the same. Can that work for sound also? Yeah,
Yes.
it can work for sound also. The idea is same. But now the range and the wavelength and etc. they will be different. So because of that, antenna size and etc. will be different. Material will also be different. The glass, the James Webb Telescope glass, might be working very well for optical light, but may not be the good reflector for the radio waves or X-rays and so on. Those things are there. Yeah, so some of the instruments are mentioned here, that our humanized instrumentation. Photographic film, you know that we used to take a photograph. That is also a kind of detector for you. You are collecting the light, you are dispersing it, and then you are recording on the photographic plate, right? So those kind of instruments, but the recent one, the most advanced one, are the charge coupled devices. This is what we are using, called CCD camera. And so. So they work on a very simple electricity principle, charge coupling, right?
Array of charging capacitance.
Right.
Even like the multispectral band.
Right. So this is what they are using as electronics in their instruments. This is a part of all the advanced instrumentation these days. And this is just a picture to make you feel excited. You can see how big the mirror is. The person is standing there, right? So it is much bigger than the person of 1 meter. It is 8 meter in diameter. You can see how clean it is looking, its surface is looking, right? Because even a small roughness, which is of the order of wavelength of light, let's say, you really defocus your light by a large amount. You really need a very, very clear, smooth surface. These are some of the instruments, CCDs. This is how they look like, right? It's a panel of electronic circuits, right? These are basically resistors, which work on the principle of charge, capacitor coupling. This is an important diagram. This is really an important diagram. So what is happening here? You are collecting the light and you are focusing it. This is the job of the aperture telescope. Now everything else is part of instrumentation and recording. So now this is going to your eyes. So what you are doing, you are using a collimating lens. So light goes parallel to your eyes. What you are doing now, you are putting a prism to it, so that you do the dispersion. So this is an instrumentation. And now finally this will fall onto photographic plate, let's say, and where you will record this spectrum. So this experiment we also did in our masters. So we had a copper source, copper wire. Those two copper wire were conducting at very, very high voltage and electricity, and then they used to produce the spark. That is the kind of radiation they emitted. And that radiation was having the properties of the copper element itself. So we'll collect that spark. It will go through all these lenses, collimator, and prism, and finally we will get a spectrum. And we will analyze that spectrum, do the calculation to find out the
Spark would know the property of the air between those two atoms,
yes.
not the copper.
Oh, I'm sorry. I'm really sorry. Yes, it will be of the property of the air itself. But then sometime you may have some copper getting but that is negligible. I'm sorry. Yeah. So it's a kind of copper arc, so which is basically ionized. Yeah, so that is ionizing the air. Same kind of thing. Thank you. So radio telescope, let's avoid that because depending upon the frequency range and wavelength range you want to look, you will design that kind of telescope and instrumentation for you. So not only this, not only the visible and radio, there are different kind of observatory and the telescopes available: ultraviolet, X-ray, gamma ray, and so on. Chandra is for X-ray. I put those photographs for you. So this is Chandra X-ray. That is Chandra or Chandrasekhar. It's really an honor to have a telescope after him. This is an X-ray satellite. By the way, for gamma ray and X-ray, you really go to this space. While for optical and radio, you can do things from the Earth itself. Why?
Because they are easily scattered in the atmosphere.
Yeah, Earth atmosphere does not allow them, right? So we have to go to this space for X-ray and gamma ray spectroscopy. And they are also called as the high energy astronomy. Why? Because they are coming from the deeper part of the matter, the radiation coming from the nuclear transformation. We call them high energy, nuclear energy. Yeah, for that we need to understand the atmosphere of Earth. There are different layers and there are plasma and so on. We really have to check why they do not reach us. No, it's not that. It's not completely true. We'll discuss that. It also depends upon the wavelength and the kind of medium they encounter. High energy also means that they will be interacting more. So they will lose their energy. They will not reach here. Simple logic. If something is very, very high energy, there are two kinds of boys. They have to return home. One guy is very quiet, so he will come home, right? Another guy is very, very energetic, so he will not come home. He will go there, he will do this, so he will fight with him and so on. The things are not very, very straightforward, right? It depends upon the intervening medium. Sorry?
They will scatter more efficiently compared to low energy.
You can see. What is the scattering? How do you understand the scattering?
The cross section.
Right.
Is very less
Right. So this is JWST, picture of that, which will be the successor of Hubble telescope, right? This is supposed to look deeper than the Hubble telescope.
So is this infrared or ultraviolet?
This is IR mostly.
The JWST, no, this should be optical. Yeah, because they are overlapping, but I think this is for optical and maybe some UV and IR, close to that visibility. I think these are Hubble telescope and JWST are the optical telescope. Fermi, these are the gamma ray, X-ray and gamma ray. This is Spitzer is the infrared telescope. But the problem with infrared is because they are related to the thermal radiation. So you are building a telescope, but then there are other things which are at temperature other than this. So they are also radiating. So now you are picking the signal not only from the true source, but also from the sources. So really don't know. And the radiation from this could be much, much stronger than the actual radiation. So you really have to shield the detectors against those temperature of the instrumentation environment and so on. But this is really the case with all the other detectors also. All those detectors, they have a huge noise. The noise could be because of the natural processes, could be the environmental glitches, could be the instrumental glitches and so on. I'll discuss the GW telescope and then we will understand more. It is really signal to noise ratio, which raises the need of the data analysis. Because it's not that you are looking for the signal that, oh, it is looking sine, so this kind of wave is coming. No. If you look at the pattern, you really don't see anything. It is a signal buried in the noise, which is totally a random signal. But now you have to use this method taught by Amit, that how you really do the analysis to find out which model fits with this random data you have got. And the data could be in the form of time series, it could be the spectrum, it could be the photographs, images, and so on. That's why the use of statistics becomes very, very critical in astronomy. So most of the time, signal to noise ratio is 1, and sometimes less than 1. You really don't know what is happening there, so you have to apply those methods. Even in the optical telescope, right? The light might not be coming from one star. Light is coming from different star. You have to keep that knowledge also and cancel that light so that you could be sure that the light you are getting is actually from that star, coming from that direction. So in the radio astronomy also, it is even difficult. If I'm doing some experiment here with the radio waves, and somebody is doing experiment in this another lab or another room, then the signals can interfere because the wavelength is of the order of meters. So if I really want to shield any kind of interfering radio signal, then I have to really be at least kilometers away. So that's the reason we made these observations which are really away from the population and so on. And otherwise, those signals also be picked. These are some photographs. This is for radio astronomy, right? You can see the antenna, radio antenna there. We know that in the radar, we use basically the radio signals. We send those signal, they get reflected back, and we analyze the reflected signal, compare it with the sent signal to infer the properties of this object which it has reflected back from.
Was that under reconstruction?
Sorry?
Was there any reconstruction done for that satellite? And it collapsed, no? Not the satellite, this radar dish.
Yeah, they unfortunately, they have a lifetime. Yeah. RCBO is also gone. Sorry? Yeah, RCBO is gone. But it was really, really very, very successful satellite. Right? People have had lots of emotions. But that has to go. So yeah, there are some satellites which they take the data over flight also. You send the balloons, you take the aircraft or maybe airplane and so on. Right? So all those techniques are driven by the kind of environment we get and so on. Right? So this is infrared astronomy. Sophia. So let's not go into this. Let's quickly come to the GW detector, which is completely different from these detectors, right? We really don't depend upon the gamma rays, X-rays, and radio waves and so on. What we depend upon then? Gravitational waves, right? And we really don't need to make any reflector or refractor for that. So what will you do now? People said that there are gravitational waves. Somebody wrote something in the chat box. With how powerful the GW is said to be, can it provide a better answer to the? Yeah, that is under debate until, because there is sensitivity, estimated sensitivity. You prepare a telescope that up to this volume or up to this length, this will be able to probe. But when it really comes to the operation, that sensitivity goes down because it might come across some accident or something, something is not working as desired. Yeah, those. I think it met with a collision.
Just a few days ago.
Yeah. So that depends. Lots of depend on what will be its operational sensitivity at the end. Right. So GW. Yeah. So yes, let me go a little slowly. We are already over the time, but let's take 10 minutes. This is interesting thing. So what kind of gravitational wave detector you would like to design?
Interferometers.
Interferometer. How do you know that? Can you erase everything what you have learned from how do you know that interferometer will work? Why do you know that
Sir,
a
because
reflector will not work?
gravity.
Because the only thing, if you want to measure something, that the quantity that is changing, we want something that would change with the whatever phenomena that is happening. So the change in gravitational field should be met with something that varies with the
Since gravitational waves are perturbations in space-time itself, uh, two clocks or anything which are separate, which have two different space-time coordinates, they will what's the word? They will register different observation values for observation of the gravitational,
There will be time dilation.
and we can
That is one way.
compare the results.
That is one way. You want to use the two clocks separated in space, right? In space.
and this is time using time, and the space version of it is interferometer.
Yeah. So the first idea is I can maybe rotate it here. So the first idea is, can we use the clocks? Very good. But before that, can we use the marker? Is the board visible to the online people? Okay. We can have the clock. What else? Any other ideas?
We can consider, and since time is equivalent to speed, we can use tape measures.
Yeah, he said that interferometer. We can't use reflectors. Why?
Because under influence of gravity of one, so and the entire Earth is experiencing the effects of gravitation. If something is changing, and this thing is also changing at same rate, how will you change the difference between those?
Or we can talk about in general relativity, the coupling of gravitation with matter is minimal. So it would be very rare for matter to reflect gravitation.
Yeah, so this is the first thing. This is really important. Interaction of GWs with matter.
The scattering cross section should be
We discussed that in the beginning of the telescopes also, that to measure the light, to record the light, we should also know how it interacts with the matter. Then only we can choose what kind of detection scheme you are trying to go. So this is clear. Interaction of GW with matter is very, very weak. So reflector may not work. Why?
because you need to interact very strongly to
Exactly. It may
invert the
not,
momentum.
yeah, it will be reflected because it's a wave. It will be reflected, but not in the way you get the electromagnetic wave reflected.
And since interferometers themselves are at sensitivity of 10 to the minus 18 or 19 meters, the kind of sensitivity you would be required to
Yes.
have for reflectors is
Yes. So the most important thing is that what are the sources of gravitational waves? Because that will tell us that what will be the amplitude of gravitational wave which we can detect.
How much sensitive?
Yeah. And the answer is it is very, very weak. Right? So no man-made source or earth-based source can produce the gravitational waves which are detectable given the current technologies. For that, we have to depend upon the astronomical objects. And even that, even the most violent astronomical event will produce the gravitational waves which are very, very weak to detect. For that, we really need to push our technology, computational limits, mathematical limits to the extreme. What kind of detector we can have? We can have any kind of physics principle. People develop, as he said, they try to develop the clock also.
I think there was a
But the
scientist
time
in
dilation will be so small that again you don't have that precision. The time
the 60s, there was a scientist called Webb or something.
Weber.
No, not- he was basically one of the first people who tried to detect gravitational waves, but instead of using these guys, he looked at molecular bonds and changes in molecular bonds.
Bar detector. So, you know, whenever some waves pass through it, it will also perturb your normal modes of vibration. So they try to detect that also. That like the sound wave. When the sound wave passes, it basically vibrates, makes your building vibrate.
So like.
So the idea was also like that. Sorry?
Yes, we have to wave a mechanical or longitudinal.
Yeah, that the example I gave could be a mechanical, but the same thing. Don't you think that electromagnetic wave, when they pass through a matter, they will also make your atoms and molecule vibrate? They can.
Yes.
Even they do, like.
Yeah.
Sun.
So wave think wave in terms of energy and momentum, not in terms of whether they are mechanical or electromagnetic. Waves carry energy and momentum. So
Yes.
whatever they see, they will transfer their energy and momentum. Now weak coupling का मतलब है, the weak coupling means that they will when they pass through the medium, they will displace those particles, but then when they travel through, the particle will come back to their original position. So that's a roughly way to understand that the weak coupling is very, very weak. So no energy, particle did not take any energy, or the wave did not give any energy to it. बहुत कंजूस wave है, right?
And even if it did, it would be generations of humans before we would be able to measure what kind of energy it will.
Right. So apart from all those schemes people discuss, tried, and the most reliable and successful technique came out to be the interferometry. That's what we are going to discuss, right? The laser interferometer, which work on the principle of Michelson interferometer. What is that? That the interference pattern is function of the path difference, and path difference is related to the phase difference. That's what we are going to explore here. So as I told you, the gravitational waves, they are the prediction of Einstein's relativity, right? As Amiya was saying, theoretically, you can think them to be the perturbations over the.
So like, we are interacting with the laser in the center parameter.
We'll come to that. Right. So the gravitational waves, they are basically ripples in the curvature of space-time. Why there will be curvature? Because of the mass. That's how the Einstein described the gravity. Right. So the way we get the electromagnetic waves from the accelerated charge particles, we will get the GWs from the accelerated masses. Right. And we know that not all the masses will radiate, but the masses which correspond to the quadrupole moment, they will radiate. Like in the electricity and magnetism, we get the radiation from the dipole only. We cannot get from the monopoles, right? That's why we say X oscillating electron. When it goes up and here, it is changing the electric field. Negative charge is here now, it is lesser here, and so on. It's changing in time. It's a kind of dipole for you, right? So we get it from this kind of system where you have two stars, two very compact stars going around each other. And why compact?
Because only then we would have high energy density.
And the high curvature, basically. So sources of gravitational waves, we will discuss one example, not all. There are several sources, but we will discuss. And most of the sources are, as I told you, are the astronomical sources. We cannot create any source which can give you the gravitational waves here on the Earth. And then we will discuss how they are detected, and finally what we can learn from the GWs. Only 4 slides. So this is the source of gravitational waves. The two objects going around each other, spiraling around each other. So these two objects could be either two black holes or two neutron stars or one neutron star and one black hole. And they are compact because their mass is of the order of sun and much, much larger than sun, but their size is very, very small compared to the sun. The radius of the neutron star is of the order of few to tens kilometers. So now see what is it? What could be the density? So the LIGO detectors, which are laser interferometer, basically for the gravitational wave coming from these kind of sources. We call them compact binary coalescences, CBCs in short. So they have three phases: in spiral when they are going around each other, merger when they jump into each other, and finally ring down. Because when you get one object, it still has some vibrations left to it, which are there again radiated away in the form of gravitational waves. So all these three stages, they reduce the gravitational wave. And finally, you get a quiet black hole, right, which has no energy left. So this is the principle of detection of gravitational waves. So this is the ring of test charges. So each black dot is basically a mass, a test mass. So they are originally arranged in the circular ring. But when the gravitational wave passes through the plane of this ring, which is perpendicular to this paper, then this is how this ring changes its arrangement or configuration. For one half cycle, it gets stretched in one direction. For second half, it gets stretched in the perpendicular direction. There are two polarizations of gravitational waves, plus and cross, because of their shape. So what is happening when the gravitational wave passing? So you can assume that these test masses, they are free particle and they are located in this space. Why they are getting stretched in space is squeezed? Because the space-time is also getting stretched in space because of the gravitational waves. So when the gravitational wave pass through the space-time, they produce strain. Strain is delta L by L. So originally there was the diameter L, and now when it passes through, it stretches the wave. So it is like this. Initially it was circular, and when the gravitational wave passed, it became elliptical. So this is the delta L, and this is the L. L by delta L will give you this strain. And the sensitivity is very, very weak, 10 to the power minus 22. Right? So now what is the scheme? That you put a mirror at this point, at one of this test mass, and another mirror perpendicular to it in this direction. And you put them at as far as away possible. Why? Because you want to make L to be very, very large. And because the strain is constant, delta L also will be very, very large. So you want gravitational wave to produce the strain or the change in length, which is measurable. And how is that possible? By making the L very, very large. You cannot do anything about strain. That is the property of space-time and wave. 10 power minus 2, it is going to be like that. But if you can make L to be very, very large, then you can get relatively larger delta. So you put one mirror here, another mirror here. So initially they are at the two ends of this cycle. So they are at the same length, same distance from the center. So you send a light, laser light, from here to this mirror, it will get reflected, it will produce the interference pattern. But when the gravitational wave passes, this gets stretched, another one gets squeezed. So you get a path difference between the two mirrors. And that will change the interference pattern. And you will say that you have detected the gravitational wave. That's the idea. So this is the interferometer. So these are the two mirrors which are at 90 degree. Their arm, the two arms at 90 degree. So this is the laser source. You get the light. You'll get the light from this laser. You get the beam splitter, which sends the light in two perpendicular directions. Light travels in this direction, gets reflected from this mirror, comes back, and because the path length is same, light travel L here, L there. There's no path difference. So you will get a dark fringe, dark spot here. Right? Whatever that you can choose. Yeah, they will be dark by but you want to put it dark, right? So that if you get any light, you can
Then
see
we
it.
beat it.
So this interference goes to this light detector. And this is basically photodiode. So it converts your light into electric signal. So what you get eventually, you get a voltage signal as a function of time. This is the time series data. So tell me, what is your telescope here? What is your instrument? And what is your detector? Ultimately, what is recording? So this whole thing is called as the detector. But this is finally recording. The photodiode recording. What instrumentation you are doing? This is the instrumentation. What you do, this one arm length. Do you know what is the length of this arm?
4 kilometers.
4 kilometers. But why cannot you make it larger than 4 kilometers?
Earth's curvature.
Earth curvature. Because light has to travel in the straight line. It has to fall on the mirror and come back. It has really traveled a very large path, long path, 4 kilometers and come back. Now imagine the precision. It has to fall that mirror which is 4 kilometers away from here, and it has to come back to exactly same point. If you do it in the air, then you are gone. So you have to create a 4 kilometer long vacuum, ultra high vacuum. There should be no particle to deflect this laser.
I can't even imagine the kind of shielding they will have.
So 4 kilometer here and 4 kilometer here.
So even 4 kilometer would introduce some. They had to
Yeah, but that is manageable.
completely flat out that whole process.
The detector is not on the ground, so they can manage.
वो उसको उतना adjust कर सकते हैं कि ठीक है mirror के ऊपर रख सकते हैं. And these mirrors are also very very big mirrors. They're very heavy mirrors. Yes, weight of one mirror is 45 kg.
Sir, I'm not sure what the following sentence means. I had read that the mirrors are suspended somewhere. What does that mean?
Yeah, mirrors have to be suspended because as Aziz was saying, because they are connected to the earth. If they remain connected to the earth, then yes, they are basically picking up the seismic activities of the earth.
Connection is shielding, so that's.
And not only that, they are also not free fall particles now. This picture is for freely falling particles, right? If Earth is putting lots of, but that will be same for this and this mirror. But the main reason is so that it does not take the seismic activities. And this also makes it a free particle, right? Freely falling into Earth. So now see, the principle is simple, but then there are noises. So if somebody is taking his or her car, then that may also vibrate the earth, and because the isolation is not that very good, so that will also, oh, we detected the gravitation. Or some aeroplane passes by, right? It can also create some vibration in the mirror, the earth. And I can tell you, with this sensitivity, you should be able to measure the length of the order of 10 to the power minus 18 meter, which is 1000 times the size of the nucleus. And you know, the seismic vibration, they can create the delta L of the order of 10 to the power minus 6 meter, minus 12 meter. Now you imagine, you have to really reduce, you have to really come down by the 12th order of magnitude, not 12 times, 12 order of magnitude. So the noise is 10 power minus 6 and signal is 10 power minus 18. Seismic. What are the other noise?
Almost anything.
Environmental and instrumental. They could be occasional, right?
Any other
Yeah, even
Because they are occasional, that's the problem. If they are continuous, then we can filter them out. But they are occasional, so we don't know when they will come, how large they will be.
even the quantum noise will create.
Exactly. Quantum noise. Before that, there is the thermal noise. Because these measures are continuously being shown by the laser light, so they will get heated. And because of heat, the particles on the surface of the mirror, they will do the larger Brownian motion. And because of that, laser light will sense that, oh, there is a change in the path length. Because mirror may move forward, mirror may move backward, and you can see that you can confuse that also with the gravitational wave. The seismic noise, thermal noise, and then there are quantum noise. What is the quantum noise? Because laser, you know, it has an energy. So the mirror is being bombarded by so many photons. Now we will see light as a particle. So mirror is being bombarded as lots of photons. So they are doing the momentum transfer. And because of that, mirror will shift. Radiation pressure noise. Another thing, that because the number of photons emitted per unit per second, it is not a constant number, it's a statistical number, right? You can calculate the intensity of the laser, you can count the number of photons. Let's say it comes out to be 10 to the power 20 per second. But are you getting exactly same 10 power 20 every time? No. Sometimes it is 1 into 10 power 20, sometimes it is 0.9 into 10 power 19, and so on. And because now you are getting different photons, so you are getting different light also. So again, your photo detector will say, oh, light increased or light decreased. There could be gravitational waves. Read out now. Sorry?
They are probably normalized light. The nature of light
So normalized means
means like the distribution of photons in that laser beam. The normal distribution.
yeah, normal distribution means there are fluctuations.
Yes.
Number of photons will be maximum here, but it could be different.
Like the mirrors will only like allow to reflect the maximum things. They don't
No.
like, use the trace.
Who will tell that to the mirror? How will you control that? No, not possible. How will you do that? Mirror will only interact with the photons which are falling right now. And another instant, the number of photons could be different. Another instant, number of photons could be different. It is not exactly same. So you know the statistical error, they go as 1 by square root n,
Yes.
number of particles. So in the one way, because you want to reduce this 1 by this noise, so you want to increase the number of photons so that this error is gone. But then if you increase the number of photons, that will increase the radiation pressure. So that's why these noise are coupled noise, right? Quantum noise. Delta X and delta P kind of situation. If you're going to reduce one, you are going to increase another one. So then there is the idea that can we use the squeezed light? I'll not go into that. Okay. What is another noise? There could be gravity gradient noise also. Earth current. We can have G something here, something else here. 4 kilometers is a big thing. So if I have 9.8 here and somewhere if I have 9.79, that can also produce.
And you should not assume that it's a 4 kilometer long ring. Without the gravitational waves, everything is the same.
Right? Because the Earth is not a perfect sphere, isn't it? Its mass alag-alag. So see the challenges. So these are some of the noises. And this is the 4 kilometer long. There's one mirror here, another one should be here. And this is the main operational building.
The CMB communicating as a noise in this picture.
CMB does not produce gravitation. No gravitation waves have been detected in the CMB as of yet.
Yeah, so that is another scheme. There are different schemes to detect the gravitational waves. So they see that the yeah, dust. So they see that if gravitational wave over there, they will affect the polarization state of CMB, cosmic microwave. इस यहाँ से कोई लेना, right? So astronomy is challenging and it's interesting. In physics, if something is not challenging, it's not interesting, worth doing. So theoretical physics तो बाद में आएगा, पहले ये सब. So that's why, because of this noise, you need a sophisticated data analysis tools, which are based on the statistics. Because all these noises are statistics. They follow the Gaussian distribution. All these processes are Gaussian processes.
Luckily for them, they have multiple detectors.
Yeah. But the thing is that, yes, the noise could be Gaussian, these things could be Gaussian, but these instrument and environmental glitches, they will add the non-Gaussianity. And your noise is also not stationary. They will also add to the non-stationarity. We have some noise now, but after 2 to 3 months, or maybe after few days, noise could be different.
So there will be those satellites.
But non-stationarity is still manageable. It's a non-Gaussianity which is problem. So had the noise been perfectly Gaussian in astronomy, then we are fine. But that's not. Yes. Because we know the theories for Gaussian noise. We don't know theory for non-Gaussian noise. That's it for today.